All right, our next video for week 7 is on analysis of variance. How do we perform this specific type of test? So first, we know that this is an F-test, and we use it when we have more than 2 means. So sometimes you're going to hear it called an F-test for ANOVA. You'll also sometimes hear it called an F-test for, and then you'll list however many means you have. The first step in ANOVA is our state step. We define the means in words. We identify our hypotheses. We identify our level of significance. Just like that test for the correlation coefficient, for ANOVA, the hypotheses are always going to look the same. The null is a statement of equality, mean 1 equals mean 2 equals mean 3, and you can write that with symbols like I did here, or you can write it with words. All of the means are equal. And then the alternative is always at least one mean is different. And you're going to see that wording because ANOVA will tell us that there is a difference somewhere in that set of means. It's not going to tell us which one is different from the others. So all we can say with ANOVA is that if our p-value is small and our sample's way out in the tail, there is at least one mean that's different in that group. For the plan, we're going to identify this as ANOVA. We can say ANOVA F-test or an F-test for however many means we have. We're going to pull the degrees of freedom for the numerator and denominator. And that's all you need to do for the plan step. We're going to assume that the conditions for this test have been met. And you can see in tiny text here, there are quite a few. We're assuming that all of the populations are approximately normal, that the samples we pulled are independent, that the population variances are approximately equal, and that we did random sampling for each of our samples. We don't have to do that for this class. If you are a practicing statistician, those are things you would need to ensure before you started your sampling. So for us, just that first line, ANOVA F-test, give me those degrees of freedom. For the do stage, we're going to use the ANOVA function on a calculator to calculate the test statistic and p-value, and then draw an appropriately labeled and shaded F distribution. The nice thing about ANOVA is it is the same function call on both the TI-84 and GeoGebra. There is no difference. For conclude, this is going to look like the conclusions for all of our other hypotheses. One sentence addressing the null, one sentence addressing the alternative. So let's really quick look at those function calls, and then we're going to do some examples. So on the TI-84, first you have to make sure that your sample data goes into lists. So for these ANOVA problems, you're going to be given sample data instead of statistics. You need to enter that sample data into lists. So first sample goes in list 1, second sample goes in list 2, and so on. Next, you're going to call ANOVA, which is in the stats test menu, and it should be the very last function call in that menu. So you're going to go all the way to the bottom. You're going to enter the list name separated by commas, and then press enter to run the command. You have to do this because unlike all of the other tests, even with the newer operating system on the TI-84s, ANOVA just pops up on your screen with no prompts. So you're going to need to enter those list names by hand. So to pull up list name 1, you press second 1, and then you press comma. To pull up list name 2, you hit second 2, and then you press comma, and so on until you have all of the means, or all of the list names entered into the ANOVA command. The upside, and this is for GeoGebra, and I don't know why I didn't type that there, looks identical. You're going to enter each list into a sample. You should give each list a different name, A, B, C, L1, L2, L3. And then call the ANOVA function. And it's ANOVA and then list names separated by commas. All right, so let's go ahead and do these examples. So example 1 says there are multiple variants of the virus that causes COVID-19. The length of hospital stays for patients afflicted with various strains of COVID-19 is shown in the table on the right. State whether the mean length of hospital stay is the same or different for the various strains of COVID-19. Construct the ANOVA table, find the p-value, and state your conclusion. Use an alpha equals 0.05, a 5% level of significance. And I can see here they've given me the data table. I can see I have 5 categories, 5 samples, 5 different populations I'm comparing. And each of those 5 have 3 data values in them. In the word problem, some clues. It says test whether the mean length of hospital stays is the same or different. And I have more than 2 means, so I know it's a test for mean, and I have more than 2. That is the clue that I'm doing ANOVA, even if they didn't mention an ANOVA table. Another warning is sometimes the textbook is going to ask you for an ANOVA table. You do not have to do that, because we are not going to be doing any of this calculation manually. If you read the textbook, it walks you through how to find a lot of the values from the sample data that we need to run ANOVA. Nobody does ANOVA by hand. It's 2025. So you can skip that part, but if you're interested, it is in the textbook, and feel free to read over it. We're just going to perform our state plan do conclude for ANOVA and let the calculator do the heavy lifting. All right, so state, we define our variables. So mean 1 equals population mean hospital stay for Delta patients. And then I've got 4 more groups. So mean 2, mean 3, mean 4, mean 5. And the only thing that's different is the variance. So I'm going to make these little quotations here, because this is the same statement over and over again, mean hospital stay. The only thing that's changing is which patient we're looking at. So the second group is Omicron. Third group is Alpha. Next group is Gamma. And last group is Beta. I know for the state step I should also identify my hypotheses and identify my level of significance. So my hypothesis is that the means are all equal. And I know that my alternative is that at least one mean is different. This problem was actually nice enough to give us a level of significance, so we know it's 5%, 0.05. Second step, I'm stating that I'm doing an ANOVA F-test. And I'm going to identify my degrees of freedom, so numerator and denominator. For numerator, I know that looking here, I've got 5 samples, k is 5. And I know my numerator is k minus 1, so that's 4. For my denominator, I need n minus k, and n is the sum of the sample sizes. So 3 plus 3 plus 3 plus 3 plus 3, because I've got 5 samples. Each of them has 3 in it, which should be 15. And 15 minus 5 is 10. So my degrees of freedom for the denominator should be 10. I'm also in the table going to write which list I'm putting these in. So I'm putting delta in list 1, omicron in list 2, alpha in list 3, gamma in list 4, beta in list 5. And then for the do stage, I just run the ANOVA function call. And it's going to give me the test statistic for F. It's going to give me a p-value. Yeah, that didn't work quite like I wanted it to. Try that again. All right, so I want to get this data in a calculator. And now that I have my data in lists, I'm going to go stat, tests, all the way down to ANOVA. And you'll notice it just prompts me. Ooh, I shouldn't do it here, however. I should go back home. Stat, tests, ANOVA. It just prompts me for list names. So second 1, comma, second 2, all the way out to list 5. And then I'm going to close my parentheses and hit enter. And it gives me a whole lot of information. And you'll notice you see DF factor. That's the degrees of freedom for the numerator is 4. And then you see DF for error, which is the degrees of freedom for the denominator, which is 10. And that's exactly what we said earlier. And then I can see 2 values. I see an F statistic, 0.353, and a p-value of 0.8362. So I'm going to go ahead and draw my F distribution up here. I know it starts at 0, and I know that it is right skewed, so peak is on the left, tail is on the right. And I know 80% of this curve is shaded in. So that test statistic here should be pretty close. And ANOVA tests are always right tail tests. And so we shade to the right. From here, it should feel very familiar because P equals 0.8362 is greater than alpha equals 0.05. We fail to reject the null. And if we fail to reject the null, we do not support the alternative. So there is not enough evidence to support a difference in the mean stays. swear I know how to say hospital stays for different COVID strains. So I'm going to zoom out a little. Looking at this hypothesis test, you'll notice here the setup is longer because I'm having more variables I need to define in words. But the rest of this, the middle, is a lot shorter. It's a single line for the plan step. I identify the test and state those degrees of freedom. For step 3, calculator function call, give me the test statistic and the p-value. And that conclusion looks identical to any other hypothesis test. All right, let's go ahead and try another one. So this one says 4 sports teams took a random sample of players regarding their GPAs for the last year. The results are shown in the table on the right. Use a significance level of 0.5 and determine if there is a difference in GPA among the teams. So looking at that word problem, it's asking determine if there is a difference in GPAs among the teams. So I'm looking at mean GPAs for each of these 4 sports teams. So this is population mean GPA for members of, and then that wording's going to be the same for all of them. And the only thing that's going to change is the sports team they're a member of. So our first sport was basketball. Next one was baseball. We've got hockey. And we've got lacrosse. I'm also going to identify our hypotheses and our level of significance. So alpha, they gave us level of significance as 0.05. I know my null, I'm assuming the means are equal. I know my alternative is at least one mean is different. For step 2, this is an ANOVA F test. I have 2 degrees of freedom, numerator and denominator. So going back to the table, I'm going to identify K and N. So K is the number of means or the number of samples, and I see 4. And then N is the sum of the sample sizes. And each of my samples is the same size. 1, 2, 3, 4, 5. So 5 plus 5 plus 5 plus 5 equals 20. And this looks familiar because we did this example in our last video. So degrees of freedom of the numerator, K minus 1 is 3. Degrees of freedom of the denominator is N minus K. 20 minus 4 is 16. I'm also going to come up here, state where I put the data. So list 1, list 2, list 3, list 4. So for the do stage on my calculator, I'm going to run ANOVA on those 4 lists. All so let's go ahead and pull up our calculator and do the ANOVA process. And we scroll up, we check that degrees of freedom are 3 and 16, so we probably did this correctly. And we get an F test statistic of 0.152 and a p-value of 0.927, and then 0.8 is going to round up to 1. So looking at that p-value is pretty big. If I were to draw my F distribution, I've got 92% of the data. So I'm like way over here close to the origin, and it's always a right tail test. So I am shading in most of that curve. Because that p-value is so big, I know I'm rejecting my null. Or failing to reject, sorry, my null. So because p equals 0.9271 is much greater than alpha equals 0.05, we failed to reject the null. Which means there is not evidence in support of a difference. So based on the small test statistic and large p-value, we can say our p-value is much greater than alpha, so we very strongly fail to reject the null. Which means that the null is very likely to be true. Our sample is so close to the null, there is so small a difference among these 5 sample mean GPAs that we cannot support the alternative. We cannot support their claim that there's a difference. Our sample more strongly supports the null, which is the claim that they're the same. All right, so that's all there is to ANOVA. If you have questions, feel free to send me an email or drop in office hours. We have 2 more videos for this week, which are going to follow up this ANOVA process. If we find a difference in the means, if this p-value had been very, very small, I would be able to know that one of these teams had a different GPA than the others, but I wouldn't know which one. So the next 2 videos are going to answer that question. How do I know where the difference is if ANOVA tells me there is a difference? All right, I'll see you in our next video.